All right. Let's get started with the afternoon session where we'll continue with the theme of FRB surveys and instrumentation. The first talk is going to be by Benito Marcote, where we'll hear about localizing FRBs at the highest angular resolution. Benito, I'll give you a 25-minute warning maybe.
Okay, thank you very much. Okay, thank you, everyone. I hope you had a good lunch. First, I would like to say sorry for not being there with you. I was really hoping to be there, but then, yeah, we had to cancel the flight at the very last minute. So I hope that next time we can make it there. So thanks for the invitation anyways, and for allowing me to give this talk. I will continue with a talk focused on instrumentation and how it's the application to FRBs. So in this talk, I will focus on all the results that has been done with the European VLBA network and how and why basically we can localize, why it's important to localize fast radio bursts to the millisecond level, to the very high angular resolution. So basically, we'll give 3 parts in the talk. I will introduce quickly fast reverse because I know that most of you have been already on the school, and then the previous talks has already touched the topic. But then I wanted as motivation of why we actually want to observe FRBs at the very highest resolution, and why only through that basically we can understand what are the local environments where FRBs are produced, and by that basically we can actually narrow down what are the different formation channels that can produce FRBs. And then the second part I will go through the results, and then basically my points there is like thanks to these observations, the ones that I will summarize and the ones that we are still doing, basically what we are seeing is that different environments like FRBs are produced and are localized in completely different environments, and we see and we believe that actually there are different formation channels that can lead into FRB objects. And something that we are seeing, and then still something to be proven, is if some of the most extreme population of FRBs maybe have some consistent host or environments, and then this is kind of the motivation of this talk. So again, I don't need to explain what an FRB is. You've already seen a lot during the past week and now. The 2 main points that I want to say is like, even if the field is really recent, like the first FRB was discovered only in 2007, we already know thousands of these objects. However, we only know where these FRBs are produced, in which host galaxies or which local environments, for a handful, only tens of them. So even if we know already a really large population of FRBs, we only have really very detailed information on a very few of these objects. Furthermore, we know that even across the entire population, only a very small fraction, like roughly a 4% of the ones that we know, seems to produce more than one burst. So we know that the vast majority of the FRB population is what we call non-repeating, so they only display one burst and nothing else after that. And then a really tiny fraction of them exhibits multiple bursts with time. Not periodic, but then we saw more than one. We still don't completely know why this is happening, if they are 2 different populations. We believe like probably it's still the same population, just different conditions, different lifetimes, but again, this is still something under discussion. However, we've discovered so many FRBs in such a few years because the rates are really high. So there are roughly 10 to 3, 10 to 4 FRBs detectable per sky and per day, given the current sensitivities of radio antennas, which means that there are some volumetric rates of 10 to 5 FRBs per gigaparsec, cubic gigaparsec per year. And this is much higher than any other rate as compared to the supernovae or GRBs. So that means that FRBs is truly a different population of objects. And the fact that we haven't localized most of them with enough precision led to really huge variety of different sources to explain what FRBs can be. At the very beginning, we could still even contemplate things that were happening in our galaxy. And that had the particularity that over time, until recently, until Chime started discovering hundreds of FRBs every few months, we had actually more possible theories to explain FRBs than actual FRBs that we discovered. And this is because we discovered a lot of FRBs, but then we didn't know where they were produced, which conditions were leading to this emission. And this is one of the focus where we started, and we saw the motivation of conducting very high resolution observations. We really need to know where FRBs are produced in order to understand them. In any case, despite all these theories, the ones that soon win a lot of potential was everything that was related to young neutron star or magnetars. And actually, this was really strengthened by the discovery of FRB-like emission in a galactic magnetar that was already known beforehand. And this is the only case where we've seen such an emission in an object within our galaxy. Was already mentioned before, but then this is a kind of isolated magnetar. So actually this put it in context, this kind of emissions, and then it led into strengthen this kind of theories. The interesting part of this particular event is that it was not only detected at the radio wavelengths, but also on X-rays. And actually, there were some X-ray bursts at the similar times as the radio ones. And this was actually predicted by many theories, and still many theories predict that at least many of the FRBs should have a counterpart at higher energies, either optical, X-rays, or even farther to gamma rays. However, from this one, what we saw is that maybe we are just not sensitive enough to detect the X-ray emission for most of them, because this was happening in our galaxy. If you go to a really far galaxy, we are just not sensitive enough to detect the X-ray counterpart. But again, this is something that I think we should always keep in mind on the FRB contest, that even if the entire field is dominated from the radio domain, because it's where we detected all the emission, it's something that has implications outside the radio domain, and actually something that is really interesting to search for different wavelengths and having simultaneous observations outside the radio domain. But this is not the only interesting part on FRBs. We study these sources basically because they have a lot of potential. The fact that they emit just a fraction of a second, just around 1 millisecond, and they travel such a long distances, means that that light carries a lot of information that has implications on many different fields. So a part of course, the interest of trying to understand what objects can produce FRBs, the other particularities is that by studying these sources, we can actually trace back a lot of properties from the universe, from the intergalactic medium, from the reionization history, and even in fundamental physics, because we are just measuring really fraction of times traveling like above high redshifts. And this is quite of the most interesting part of FRBs, and that's why there are many people interested on this. But again, we have quite a large population already, but we don't understand where they are produced. And if we really want to understand what can produce FRBs, we really need to understand where they are formed, where they are located, and what conditions are around it. So that's why observations like with the European VLBA network is really relevant, because for most of the single dishes, we have a really poor resolution. There are thousands of possible counterparts associated to FRBs. The fact that there is no extra emission or afterglows after each FRB means that we cannot actually narrow down and identify any other transient source associated to the FRBs. And as you can see here, just moving from single dish, even from Parks to Arecibo, VLA, equivalent to GMRT, it narrows down, but then we go to really distant galaxies, we really need a much better resolution. That is only possible with VLBI. And by that, we can trace not only the host galaxies, but actually also the local environments within that galaxy. And that's what actually leads us to understand what are the progenitors. So we only by studying the local environments of FRBs, we can actually understand how and where these events are produced. And that's why we've been observing it with the European VLBA network, which is a network of antennas, mainly in Europe, but also with antennas in Asia, Africa, even America. And then we observe at centimeter wavelengths in general, and then we can reach resolutions of the order of 1 millisecond, which means that we can achieve resolutions on the parsec scale for redshift between 0.1 and 1. And it's really good that, for example, the GMRT can actually now participate in observations within the EVN, and recently, since last month, actually, even Marcote, which means that we will actually boost a lot the sensitivity of these arrays and actually the resolution or the precision that we can achieve in these localizations. So far, we haven't observed yet any FRB with EVN plus UMRT, but then we are really waiting for it, because that will improve a lot the accuracy that we can reach in our images. And then during all these years, we've been conducting regular observations with the EVN. All the results that we will put here are in the context of the PRECISE and AstroFlash groups projects that I'm part of. And then we've been basically targeting repeating fast radio bursts, because are the only ones that we don't know when they will happen, but we know where roughly they will happen. And then the precision basically coming from chime for most of them, it's good enough to actually observe them with our dishes. And then from there, we can actually localize it, doesn't matter where within the primary beam, even if once we correlate, we have a really tiny field of view, but then actually we can reconstruct any image within the primary beam of these dishes. So what can we do with VLBA observations on the field of FRBs? Well, we can, as I said, localize it to millisecond level. That's what we did with the first ever localized fast radio burst, 2012-1102. We found that this FRB was localized into a low metallicity star-forming dwarf galaxy. And actually, the FRBs were coming from really inside the star-forming region, a prominent star-forming region there, as you can see here. Even more interestingly, these FRBs were consistent in position with a persistent radio emission, really compact, as you can see on the left image. That's the persistent emission. It's less than 0.7 parsec in size, and that's really constraining, because if you can think on different possible scenarios, we assume like this is a young neutron star, you can think that this is the supernova Ramanujan or the pulsar wind nebula, but comparing with the galactic cases like the Crab Nebula, it's already much bigger than this source. So we can put strong constraints on either the nature and the age of these systems. And actually, this looks like a quite interesting case, because we know that, for example, long GRBs are produced in this kind of systems, in low metallicity star-forming regions of dwarf galaxies. So this was the first FRB that was ever localized, and then we thought that it could be the pattern, but as we saw later, this was kind of an exception until recently. So we didn't know if there is a possible connection on GRBs forming really young magnetars and producing such an emission. But as I said, this was kind of the exception, but in the last years, we've been seeing a few FRBs that are called kind of twins of this FRB because they are in similar contexts. So we localize another FRB, like 190512, that is also in a dwarf galaxy. It's also inside the star-forming region, and it's also associated to a persistent radio counterpart. Just because this source is farther away, our limits on the size of this object are a bit poorer, but still, we know that it's a really compact source. It's less than 9 parsecs. Which means that it's already putting some constraints on the models that can explain this emission. And even more recently, this year, we just submitted another localization on another FRB, 1917, which also is associated to a persistent radio source, also really compact, on millisecond scales, and also in a dwarf galaxy. And these were kind of almost the only objects, the only FRBs that has been found in dwarf galaxies. And these ones are actually the ones that seems to have either a higher activity or a much larger Faraday rotation measure, which means that it seems like these FRBs are actually the most extreme population of FRBs. Do we expect the most extreme FRBs associated to persistent radio counterparts? Maybe yes, maybe no. This is still an open question, but maybe we are actually narrow down what's the scenario that can explain these sources and why we have this persistent emission. There is, of course, and then we can see here, this is just a plot between the galaxy, the host galaxy magnitudes, and different redshifts for different FRBs. All the green boxes are just standard non-repeating or repeating FRBs. And then the stars are the ones that I just mentioned, the most extreme FRBs that are actually associated to persistent radio counterparts. So you can see here that these ones are actually in the low end of the host galaxies. And we only have 3-4 of these systems, so we still cannot trace any statistics, any proper statistics here. But maybe this is telling us that the most extreme FRBs are actually located in these low metallicity dwarf galaxies, and probably associated to some either young nebula associated to them, or because they are in a more extreme scenario. There is only another case, two cases where the FRBs are also associated to or are found in dwarf galaxies, but without any persistent emission. And one of them, 1902-08 on the left, is actually the dwarf galaxy is even way fainter, way smaller than any other one by 1 order of magnitude. And recently, we just submitted another one where the FRB is actually in a satellite dwarf galaxy from another companion or main galaxy. But what this is telling us is actually that not only having a sensitive radio surveys to detect FRBs are critical, but also having really deep optical emission, optical telescope, optical images. Because as you can see here on the right, the dwarf galaxy where the FRB was localized, it's really faint in the optical. And actually in the previous case, in this one, the galaxy was not even detected in most of the images that we had. So you really need deep optical surveys in order to find the host galaxies in some of these FRBs. But once you have that, and if we really have millisecond resolution, we can actually put, as I said before, as you saw, really steep, strong constraints on the sizes. And this is the way to actually try to explain what these objects are. We don't know if there is the same object producing the FRBs, or it's just some object that is collocated with it. But due to this compactness, we can actually try to narrow down both the edges and the nature of these systems. So for example, this is a particular case where we actually, thanks to these observations, we can see and we can really limit the possible parameter space under the magnetar with nebulae scenario. And you can see here how we are actually constraining the age of these systems to be really young, which goes consistent with many of the theories that we have. But again, as I said, is the question about if the FRBs and the persistent emission are the same object or different ones in the same, happen to be in the same position, is still open. The two more prominent scenarios is where we have a magnetar with nebula or a superluminous supernovae. And of course, we have the magnetar inside it. So that's why they are collocated. But then, given that we are seeing many of these ones in dwarf galaxies, we know that these systems may have a potential number of intermediate or just almost stellar mass, intermediate mass black holes. So it seems reasonable, and still it's possible that we have a magnetar just orbiting this kind of systems. And the persistent emission comes from the whole system itself. However, this is just a very tiny piece of the whole history on the FRBs that we know, because these are selection of the ones that are in dwarf galaxies. And whereas all these ones can be explained by the similar list scenario, we know that some FRBs are in a completely radical different scenario. So for example, the second FRB that was localized, 1809-16, was found to be in a spiral galaxy similar to the Milky Way, but they're still quite close to a star-forming region, which is kind of a pattern in many of the FRBs. As you can see here, the tiny green dot is where the FRBs are coming from. And the color image is just the optical image from the Hubble. So as you can see here, the FRB is actually outside this star-forming region, which means that under the assumption that this is a really young object, it should have been formed inside the star-forming region. So it requires quite a significant time to travel away from this region. So the only possible to have a young neutron star or presumably active magnetar here is that it's located in a binary system. So you may need a companion star that acts actually speeding up and refueling these systems. So this is actually, in addition, the only FRB that seems to have a really clear period of activity. So every 16 days, there is a window of around 4 days where the bursts are produced. And this is really constant and periodic with the time. So we've been observing it for years now. And then we see that this activity is really persistent. So this also goes in favor of this kind of models where the FRB is produced within a binary system, because 16 days seems to be a reasonable orbital period on this kind of systems. And we've been seeing that most of the repeating FRBs, or many of them, are associated to star-forming regions. But we have so far only one exception, which is this FRB, 200120, which was actually localized in a global cluster. So there is nothing really young there. And that's why we believe that there are different formation channels that may lead to FRB emission. This FRB had other particularities, like so far is the ones where we detected the narrowest emission. So far we have subcomponents within a burst that are as narrow as 60 nanoseconds. And here we are just limited by the instrumentation. But then we see that there are different properties in different FRBs. And then I will just start finishing here. One thing that I want to highlight above this is that if you think on FRB searches or FRB detections, you have systems that you don't know when they are happening, but then you need to keep observing. So even with all these detections and results, you can keep in mind that FRBs require a lot of observational efforts. So to put in the context, within the PRECISE project, we've been basically spending thousands of hours. We've been localizing several FRBs, but then if you add the signal, the actual signal from FRBs, it lasts for less than 1 second, which means that FRBs require a lot of observational time in order to produce results. But when you have it and then you detect the FRBs, you can get the precise localizations, as you saw in the previous slides, temporal resolution. And I haven't mentioned in this talk, but also you can get some accurate energy distribution of the bursts. And with that, I will just go to the conclusions. FRBs is still a really exciting field because there is a lot of opening questions. Observations with VLBI are, in our opinion, key to understand the local environments, so to try to narrow down the formation channels that can lead to FRB production. And so far, we've been localizing FRBs on millisecond level. Since this year, CHIME is already localizing almost at the same level on the tens of milliseconds, and other instruments will come forward. But then instruments like the EVN, especially now that it gets in combination with GMRT or even Marcote, we can actually achieve micro Jansky sensitivity and millisecond resolution at the same time. And right now we are going through trying to get more localizations of these FRBs, especially if we can find more FRBs associated to persistent radio sources, because from here we think that we have much information in order to understand how these FRBs are produced, because we can actually study this persistent radio emission and put stronger constraints on it. And with that, thanks everyone for listening.
Thanks for your talk, Benito. Questions for the speaker?
Hi. So if you find more FRBs, more extreme FRBs in dwarf galaxies, the number density of dwarf galaxies is supposed to be huge, right? So ideally you should find more such cases. But that is not what is happening, right? Another thing is, but even if you are right, then there is a possibility that there are some interlooper dwarf galaxies which are found in other localizations. What is your opinion about it?
That's a very good question. Indeed, if we go to dwarf galaxies, the number would be really huge. Even if, I put the samples, and those are the only ones that have been found in dwarf galaxies, if you think that there are hundreds of FRBs localized, this is a really tiny fraction. So we think that the key point here may be the lifetimes on FRBs. That is something that is really poorly constrained, but of course the key point is like how long these FRBs may last on these particular conditions. Just to put one possible scenario, which is not the most promising one, not the only one, it's just one of them. Let's say that, for example, they are associated to just a very young magnet that was produced there. Maybe the lifetimes of this, and this is why we still have the persistent emission there. Maybe the lifetime of this is really short. So that means that even if there are a lot of possible hosts where these FRBs will produce, the number of ones that we can detect are really few of them.
Okay, thanks.
Any more questions?
Thank you. Very interesting talk. Just a comment about this last point. The number density of sources that have persistent emission, so say something like 121102, is absolutely tiny. It's about 1 per gigaparsec cube. So taking that into account, the selection process of going from star formation in a dwarf galaxy to actually having one of those sources is extremely refined. So it's, even if you take into account the fraction of stars that end up as magnetars and the fraction of them that are young enough, let's say tens of years or something like that, to produce a persistent source, even that will be too abundant. You actually need to be more selective than that. So we have to keep in mind all the time that these are very, very rare sources. Those sources that we see as persistent sources, they are intrinsically very rare. And there could be there must be additional selection effects going on between the intrinsic population and what we actually see.
Yeah, exactly. That's, I think, the main point that we structured from here. Like, we know this is a tiny one. It's interesting to study them in detail because it seems to be the most extreme environment. So that's why we are putting special interest on these ones. But indeed, this is a really tiny fraction and really selective fraction of the entire population. And the other one that it's even more goes into the selection and why we don't detect more of them is, like, if you think on dwarf galaxies, this is really faint systems. So for many of the FRBs, once they are beyond a redshift 1 or so, it's likely that we will never detect this kind of emission from there. And that actually goes to some of the FRBs that seem to be hostless, actually. But again, this is really a tiny fraction.
Thanks.
Any other questions? Maybe I'll ask one more. Again, on the same thing of like evolving or like increasing population of FRBs with PRS sources in dwarf galaxies. For those particular candidates, can you comment on whether or not their RM or DMs seem to stand out when you compare it with non-repeaters?
Yeah, so the ones that were treated to PRSs in dwarf galaxies are actually the ones that show a really extreme RM. So the two first ones are the only ones that have RMs of 10 to 4, 10 to 5. And then the other one is still like hundreds, which is remarkable. I mean, way less than the previous ones, but it's still much higher than most of the FRBs, the rest of the FRBs that have been localized. And all these ones exhibit variations on DM. So a long time, still some of them, it can be like higher and down. There seems to be trends, but then still we don't see any like clear trend if it goes down with time or like it's just going up and down on different time scales. But indeed, we talk about these ones as the most extreme cases because the RM is way higher than in the other FRBs, which is already telling you that that environment must be more extreme.
I see. Thanks, Benito. If there aren't any other final thoughts or questions, let's just thank our speaker again.